In September 2025, physicists made a surprising announcement. They discovered a new type of time crystal. No, it's not a totem you wear around your neck to heal yourself from diseases, and it's not something that breaks the laws of physics, as some often say. I know it sounds like something out of Star Trek, but it's a rigorously documented scientific result. It's a phase of matter that doesn't just repeat in space like ordinary crystals, but also in time. Let's unravel the mystery behind it together. We'll start with what ordinary crystals are. Then we'll explain the strange concept of time crystals. Where it came from, how it was challenged, and how it was ultimately proven. After that, we'll move on to the most recent discovery, a time crystal in liquid crystals, directly visible under a microscope. Finally, we'll ask ourselves what this means for the future and what applications might follow from here. A crystal is a material whose atoms or molecules are arranged in a repetitive way, like on a chessboard. Think of table salt. Sodium and chlorine form regular cubes. Quartz, silicon, and oxygen align in a repetitive tetrahedral network. Snowflakes, water molecules create hexagonal symmetry. What's important is that these structures represent the lowest energy state of those materials. Atoms arrange themselves in these repeating patterns because that minimizes the total energy. That's why crystals are stable. That's why diamonds and quartz don't spontaneously break down. And now comes the question. If nature creates repeating patterns in the three spatial dimensions, could it also create a repetitive order in the fourth dimension, time? Normally, in the lowest energy state, the positions of the atoms that form a pattern are always the same. However, could there be a system of atoms in which, in the lowest energy state, this pattern changes over time periodically? Like a chessboard where the pattern changes regularly. This was Nobel laureate Franz Wilczek's question in 2012. In his article Quantum Time Crystals, he proposed something radical. What if a system of particles or atoms, even in the lowest energy state, could still exhibit motion, repeating itself periodically in time? This idea was shocking because normally the ground state, the lowest energy state, is static. If you let a pendulum swing, it stops at its lowest position. But Wilczek imagined that, at the quantum level, there could be eternal oscillations without any energy input. So, it wouldn't be a perpetual motion machine, because no energy is extracted from that system. He gave a simple model. A superconducting ring. Inside it, the electrons move perpetually in the ground state. In such a state, motion and minimal energy would coexist. Wilczek's example has a problem. The superconducting ring can interact with the environment, for example by orienting the magnets around it due to its magnetic field. Over time, the electric current in the ring will decrease until the motion stops completely. This type of objection was formalized in 2015 when physicists Bruno Oshikawa and Watanabe proved what became known as the no-go theorem. The article showed that a perpetually moving system in equilibrium and without any energy input cannot exist in our reality. If a system were to oscillate endlessly, it would have to be completely isolated from its environment. But in reality, everything interacts. Heat, noise, particles. The verdict seemed clear. Wilczek's dream was impossible. A system in its ground state cannot continue to move forever. Time crystals, in the strict sense, could not exist. But if we allow energy input, researchers have focused on systems that are out of equilibrium, systems that are periodically supplied with energy. At first it seemed like cheating. You put in energy, you get oscillation just like in a quartz clock. But here's the difference. A time crystal, when activated with energy, spontaneously jumps to oscillations that have a period different from that of the excitation, so it's not like a clock, where the frequency is the same. For example, You hit the crystal with a pulse every second, and it responds once every 7.2 seconds. That's not ordinary resonance. It's the system that imposes its own natural rhythm. It's almost like a time crystal. This is the difference between a time crystal and a quartz crystal in a watch. Quartz vibrates exactly at the frequency of the applied current. A time crystal, on the other hand, breaks symmetry. It oscillates at its own period, independent of the energy source. This subtle distinction is crucial, otherwise any watch would be a time crystal. Poral. In 2016, a group from the University of Maryland trapped 10 ytterbium ions and excited them with lasers. The ions began to flip periodically, not at the excitation period, but at double the period. This was the first time crystal ever observed. In 2017, a group from Harvard University used nitrogen-doped diamond. Stable oscillations appeared again, not directly following the excitation. Later, other systems were added. In 2021, Google used its Sycamore processor to demonstrate a time crystal phase that lasted thousands of cycles. In the same year, a group of German and Polish researchers managed to create a space-time crystal the size of a micrometer, made from dysprosium right at its development. With the help of an ultra-precise X-ray microscope, they managed to capture its recurrent periodic magnetization structure in a film. Time crystals were no longer just a theory. They had become real. And we come to the latest discovery. In September 2025, a group working with liquid crystals reported something extraordinary. A space-time crystal formed from particle-like topological solitons. Let's explain. Liquid crystals are materials whose molecules align in an orderly way like in a crystal, but can also move like in a liquid. We know them from LCD screens. Precisely because they combine order and fluidity, they are excellent platforms for exotic phases of matter. In the new experiment, researchers observed solitons, localized disturbances of the molecules, which arranged themselves into a repetitive network. But there wasn't just order in space. The solitons also oscillated periodically in time. In other words, the material spontaneously created a pattern that repeated both in space and in time, a true solid crystal. To work once again, the system was given energy. This came from LEDs whose light, mind you, was not even pulsed, but continuous. In other words, the few-second pulse generated by the time crystal was truly natural, entirely its own. Why doesn't this violate the no-go theorem we talked about at the beginning? Because the system is not isolated from the environment. It receives an energy input from the light. Energy flows in and out, but the oscillation is stabilized by the topology of the solitons and the symmetry of the system. It doesn't break the laws of physics. Why is it special? For the first time, the effect is directly visible under the microscope. Unlike trapped ions or superconducting circuits hidden in refrigerators at very low temperatures, these oscillations can be seen with the naked eye through an optical microscope. It's a tangible demonstration of a time crystal. What could these time crystals be used for? Scientists are cautious, but here are some of their ideas. Quantum computing. Time crystals resist decoherence caused by interaction with the environment, locking themselves into stable oscillations. These systems, once brought into a quantum regime, could serve as robust memory elements or even qubits, resistant to errors. Measurement and precision sensors. Because they naturally oscillate at stable frequencies, time crystals could be used in extremely precise clocks or in sensors that are even more resistant to the environment than quartz. New materials. Just as superconductors revolutionized technology, time crystals could inspire future devices based on phases of matter that are out of equilibrium. For now, these are possibilities, not products. But history shows us that exotic phases of matter, like superconductivity or topological insulators, end up being used in real-world applications. Let's recap. Ordinary crystals repeat in space. In 2012, Frank Wilczek proposed the idea of repetition in time crystals. Skeptics responded with the no-go theorem, no perpetual motion machine in equilibrium. But physicists found a way. Systems out of equilibrium, with external energy input, where oscillations stabilize at their own period. The first demonstrations appeared with ions, then in diamond and quantum computers. And now, in 2025, the discovery in liquid crystals, a space-time crystal formed from solitons, visible under the microscope. It doesn't break physics, it doesn't provide infinite energy. But it brings a new phase of matter, a tangible proof of order, both in space and in time. The story of crystals. Time crystals is far from over. We don't know all the applications yet, but one thing is certain. Matter can organize itself beyond our everyday experience. Not just in space, but also in the rhythm of time they choose. This was today's video. I don't sell these kinds of time crystals as pendants that heal you from diseases and protect you from harm. I'm trying to popularize science. If you also think this is useful and interesting, please visit my Patreon page. There, I can answer your personal science questions directly, and in addition, you also help to popularize science this way. Until next time, I am Christian Pressura. Physics Explained. You are cool. All the best. Goodbye.